Hello and welcome in this third tutorial for Midas Gen. In today's tutorial I will show you step by step how to design a reinforced concrete building which is subjected to floor load, wind loads and seismic loads. Also I'll go into deep details and I'll show you how to do the response spectrum analysis, how to do the P-delta analysis, and I'll start basically with the modeling and then I'll show you in function of the code how to input the parameters and how to do the design of the beams and the columns inside this building. So let's start right away. So as you can see here, I just started the software. So let's go in the menu and open a new project. Okay, so now that I'm in the new project, let's set up the units. So for this analysis I will be in lbf and inches. And let's start by defining the material and the properties. So for the material, let's add a new material, and this will be a concrete material. So let's use the code ASTMRC, and in the database we'll select grade C4000. So you get all the coefficients here. Click on OK to add that. Now let's add some sections. So I have three types of section in this analysis. So I have edge columns. So for the section profile I'll just use solid rectangle. So I have to enter the name edge columns, and the dimensions are 24 inches by 24 inches. Click on apply. Now I have the interior column, interior columns. So, and this time this will be 30 inches by 30 inches. Apply. And finally I have the beams, so I'll just change that into beams and input the size 20 by 24, and I click on OK. Now I will have some shear wall into my structure, so I have to define the thickness for the shear wall. So the thickness of the wall is 18 inches. So let's input that in here and click on OK. And I just defined my material, my section, and my thickness. Okay, so now let's start the modeling. So the first thing I'll do is I will change my my global coordinate system to the user coordinate system. But before that, let's change the unit to fit, and let's go into structure and let's set up our XY plane. So the origin will be 0, 0, 16. The angle is 0 and I have to change direction. Okay, now I get the plane. So now the second thing I'll do is I'll define some grid that will be very useful to design the first floor of my building. So you see that you have point grid and you have line grid, so I will use a line grid. Let's add that. You have to enter the name of the grid, that's 2F, and add that here. So let's use relative 7 at 26. So it will be repeat 7 times with a distance of 26. Okay, and let's do the same here with 3 at 22. And just click on OK. OK, and I get the grid here. So it's I have to put it in full screen, so I'll use the function auto fitting, which is very useful to keep always all the grid in the screen. Now let's check here that the line grid snap is activated, so it's okay. So here my menu is here, but originally when you start the software it's here. So if you don't find it, you just have to, because I switched that here. So you can do as you want, you can customize the interface. Now that I got the grid, I can start to model my first floor. So let's go in node element and let's create element. So let's create a general beam. Let's change the property to beams, and now I only have to snap on the screen like that to create my first floor. So you just have to follow me. So I'm creating like that. Then I'm just creating like that element, and you see that this is automatically intersecting because I checked these options, intersect node and element. If I didn't check that, it will not intersect. So you would have to do that manually. Okay, 1, 3, and then I have to create some small beams here and here. And that's done basically. Now that I got this floor, let's generate the column. So the first thing is to come back to my global coordinate system. So you can do that here, and then you go in the isometric view like that. So I can close this, and now I have to select all the elements and then use the function called extrude to extrude the node into line elements, reverse the IJ, and so this time I will use edge column as the property, and distance is -16. Let's apply, and as you see I just generated all the columns for my model. Now maybe you noticed that I assign the same property to all the columns, but actually the column inside I want to assign a different property, which is the property called interior column. So I will try to do that by first of all, let's display only these edge columns. So I click here to select this, and then in this small icon you have activate. So you can also use F2, it's much faster. So now I got only the columns here, and to show you that I'm changing that property, let's go into display and let's display the property name which is assigned to each of the elements. So let's go into the top view. So you see now I have edge column associated to all that. So what I have to do is use the selection by window, select the column that I want to change property, and drag and drop this property in the screen like that, and you see now the property has changed. So I have my edge columns and I have my interior columns. Okay, now let's hide this property name again. Let's display everything again, and let's select only one part. So let's go in the top view and let's display only this part here, because I want to generate a shear wall on this area here. So I displayed only that. It will be more easy to generate the wall element. So go into create element, and in the element type you have wall element. So let's choose the right thing. So this is a membrane, okay, plate base. The material is okay, there's only one thickness, so it's okay. Okay, so basically everything seems right. So let's click here, and you have to go to select the nodes in the right order, which means like that. First start with the bottom, then select like that all the nodes, and your wall element will be generated automatically. Now I want this element to be translated to the other side because this is symmetric in my building. So to do that, let's use the function translate element, and let's use copy. So I have to select again this element, so I will use select single to select my wall, and then I have to input the right distance. So of course in my case I know what is the distance, so this is 130, so I just input that, click on apply, and here well, increment ID, okay, the ID is 1. Now let's activate everything again, and you see I created at the right place my new shear wall. Okay, now that I got the first floor, let's generate the full building. So to do that, it can very easily be done. You go into structure, and you have building control data, building generation. Then select all the elements, and then the number of times you want to copy that. So I want to copy that 11 times, and the distance, which is 12 feet between the stage, and then click on add and apply, and I got my building. Now okay, now let's generate the story data. So go into story, and here you can do auto generate this much faster. So by default it automatically rename like that from 1 to the roof, which is the last of the floors. Click on OK, and you see it. You can consider the floor diaphragm, or you can not consider it for the roof, and that's done. Now that my building model is completed, let's input the boundary condition and the loadings. So let's go into the front view, and let's go in the boundary tab, define support. Now I have to select like that the nodes on the bottom, and fix the translation and the rotation, apply. So that's all for that's all for the boundary condition. Now let's close that, and before I input the loads, let's build the static load cases. So I will input them one by one. If you think that's too boring, you can pass a bit. So did load, I'll put description, okay, add. Then I have the live load. Okay. Then I have the wind load in X direction. Add. I have the wind load in Y direction. I have then 4 earthquake loads, so I will call them EYN, earthquake, because this is earthquake load in Y direction. For this is for negative eccentricity, so I will not note it like that. Add. Then EYP, eccentricity positive. Add. Then I have EX, EXN, so which is in X direction for negative eccentricity, and EXP in X direction, eccentricity positive. Add. And that's all for the static load cases. Okay, so now I can assign the different loads. So let's start with the self-weight. So, okay, dl -1 in that direction and add it to the load case. Now let's assign the floor load. So to assign the floor load, I will display only the first floor. So select like that, display, and let's view that in the isometric view. And then let's go into load, assign floor load. So first, before you define the floor load, you have to define the different load types. So click here, and I have two load types, one for the typical floor and one for the roof level. So let's enter the typical floor floor type. So DL will be -10, -10, and the live load will be, oh sorry, not -10, -30, and the live load will be -75. Add. The second is the roof level, and this time it's -10 and -20. Okay, add. Now let's add first the typical floor. So this is a two-way distribution, so you have all the type of distribution if you want, and it's in global Z direction. Important thing is that we'll copy this floor load to the other floors. So let's click on copy, and the distance will be 10 times the distance, like that, or 12 times the distance of 10. And now I have to select the 4 nodes. Okay, and my load is automatically created. So now let's activate everything again, so the small button here. So there's one thing that you may think that actually the load has been only applied to the first floor because it's only displayed like that, but it's only because it was hidden when you generated that. So if, for example, you activate the load and you display the floor load like that, you see that now it's assigned to all the floors, so which means that it works basically. So this only to tell you that, because some people are asking about that. So let's display that. So now let's assign the roof load. So to assign the roof load, let's display only the roof, like that. And so I only have to change the load type, and so I don't need to copy that, and I have to select the nodes like that to assign the roof load, and that's done. Okay, so now let's assign the wind load. Wind load is in here in the lateral type of loads. So let's click on add. So my WX load, and the code I will use is the IBC 2012. I will use the alternate method, and exposure category will be B with okay, the wind speed is okay, and then the factor here should be 0 because this is the wind load in X direction. So then click on apply. Now generate another wind load in the Y direction, so the only thing I have to change is direction here, and click on OK. Okay, Okay, now I have to create the seismic load. So before I create the static seismic loads, I have to do something. I have to convert the model weight and loads into masses. So for that, go into type, structure type, and in this window you see that you can do that. So why am I doing that? Because actually basically the self weight and the loads like that are applied on the beam so what I want is not to apply on element but apply on the nodes. So because seismic load only take in account the nodes, so I use this function to convert the loads like the self weight, for example, into nodal type of load. So you have the choice to convert into X, Y, Z type of nodal load, or you can simply neglect the Z to convert to X, Y. Because in some cases the Z is just neglectable, so I just do that. So after I do that, go into loads, and I have here load to masses, so I have to basically to do the same with the other loads. So the mass direction will be XY, that's good. Load type for converting, so I have to select everything, and now I have to select the load case to convert. So load case, the dead load, and live load with a scale factor of 0.25. Okay, so this all that is written inside the code that I'm using. Okay, so as you see the small symbol, it means that everything has been assigned correctly. So now let's assign the seismic loads. Add, and let's start by assigning the, let's say, EY-EXP for the code IBC 2012. So the site class is E. No, sorry, this is C. Yes, site class is C, and for the factor 1 and 0.3, I will use 1 for the importance factor, and then here in the approximate period enter 1.2 and 0, and the response modification factor will be 8 and 8, and here finally for the direction is 1 and 0 because this is in X direction. Eccentricity positive, so I check here positive. So I just click on apply to add this load here. So let's do now EXN. So it's basically the same, I just have to change here negative to negative for the eccentricity and click on apply. Now EYP, so EYP is, I have to inverse the coefficients here, 1.2 and 0 in direction, and here as well 0 in X direction and 1 in Y direction, and this is positive for eccentricity, so I could check positive. And the final load EYN, so same but negative eccentricity. Okay, and I just created my 4 seismic loads. So now, as you know probably, the code also required to calculate the response spectrum load. So I already defined a static seismic load, and now I have to do dynamic loading of the response spectrum load to apply that to the building. So to do that, let's go into dynamic, and here you have response spectrum data, and let's input first the response spectrum function. So this is where you can input the response spectrum, so you can directly paste from Excel the data, but also Midas Gen has directly a database of seismic data, which is very useful. So you can simply select your code and select your parameters, Click on OK, and as you see, it generates automatically the response spectrum. Click on OK. Now let's create the response spectrum load case. So my first load case is response spectrum in x direction. So okay, direction Rx. The excitation angle is 0. The scale factor is 0.125. The period modification factor is 0. Okay, I have to select the function. And let's use linear interpolation. Let's use the accidental eccentricity. And I have to check also the model combination control. But before I do that, I have to confirm the eigenvalue analysis control that I will be using. So I will use for that subspace iteration. I will check for 10 number of frequencies. So that's it. Okay. If I don't check that first, here in this window, these mode shapes don't appear. So you have to do that. And I will use the RSS model combination type. Click on OK. Click on Add. Now the second load case RY. And for this one, the excitation angle is 90 degrees. And the other things are the same. So I click on Add. And I created my two subcases. Now let's set up the parameters for the p delta analysis. So I want 5 number of iterations, and for the load cases I have to create 2 load cases, dead load with coefficient of 1 and live load with coefficient of 0.25, and that's it. Okay. And eigenvalue, I already checked that previously, so it's okay. And now I can simply click on perform the analysis to run that. So now you see the information from the analysis here in this window, and once this is completed, you will see the results. Okay, so your Midas job is successfully completed. Hurrah! So now we can go on and start with the design. So now I can have a quick look at the results. So let's take a look, for example, the deformation contour will be like that. We can also take a look at the reaction. Okay, so as you can see here, the maximum load is here in red at the shear wall. So for the moment, the analysis has been done with only concrete, so there is no reinforcement inside this building. So what I will do right now is to design this reinforcement using the design function in Midas Gen. So first thing I need to do is to define some load combination that will be used for the concrete design. So go into concrete design, and here you click on auto generation. So let's choose the code that I'm using. So I'm using AC, this one, and let's use different scale factors. So 1.48 for the Rx and 1 for the Ry. That's it. So click on OK, and now the Midas Gen generates automatically the load. So bidirectional combination needs to be investigated as well, but in this tutorial I will not take it in account, but in a real project you will have to consider that. Let's close. Now let's compare briefly the results that I got for the two analysis, the response spectrum and the static. So to do that, go in the result table, and here you have result tables, story, yes, story, and story shear. So story shear response spectrum. Okay. Select the two load cases. Okay. And you have the different story shear force coefficients. Okay, this is eccentricity, the story force, eccentric moment. Okay. Now let's compare with the EX and the EY. So to compare, I have first to come back to my model and to go into load, seismic load, eccentricity P, modify, and I want to modify the seismic load profile. So this type I will choose the story shear type of profile, and okay, and choose the story shear on. So that's it, and you have to do that. Okay, you have to change that for the 4 type of profiles. Okay, and then you can check again the result. I will not show how to do that in this tutorial because that's obvious. So now let's move on to the part where I show you how to design my concrete building. So let's go in the design tab, and let's choose first the code that I will be using, which is this one. And then in the general design parameter, let's go in the definition of the frame. So in this window you can define if you need to define braces or unbraced type of frame in X or in Y direction. So in my case I will choose unbraced for X direction and braced for X direction. So the design type is 3D, and it will auto calculate the effective length factor. So click on OK, and let's go now to modify the live load reduction factor. So to do that I have to select the different type of vertical members. So what I'll do is that I will activate the second tree menu. So maybe you don't know you can do that, but you can use this to select very quickly, for example, the edge columns. So I just double click here and all the edge columns in my model are selected. So now for edge column my coefficient is 0.69. Apply, and then for the interior column it's 0.56, and finally for the okay, and that's all. So that's all. So I close that, and I will hide again this second tree menu. And now let's check the embraced lens. So in this case, I'll just input 0, 0 and do not consider the lateral embrace lens. I have to select everything and click on apply to apply it. Now let's look at the equivalent moment correction factor, CM. So let's calculate that by the program. Okay, and now, so I selected the code here, and in this button RC design code, let's check design code. So let's apply the special provision for seismic design, and in the frame type choose special moment frame and click on OK to calculate automatically the design. Now let's check the strength reduction factor. Let's update by the code. Okay. And now we can do the rebar of the model. So let's go here and design criteria for the rebar. So now we will do the rebar of all the members. So you can see here, this is for the beam design, this is for column design, this is for brace, and this is for shear wall design. So we have to check the main rebar that we want to use. So let's say I want to use this 2 diameters. What we'll use for the stirrup and for the sidebars. So you input all the coefficients you need and click on OK. And now what we have to do is to modify the concrete material, because for the moment I have only concrete without any reinforcement. So the code I'm using is this one. So let's use also the same code, and let's use grade 60 and grade 40 for the stirrups. Click on modify, okay, to add this, and click on close. So to do the beam design, reinforced concrete design, and here you have concrete code design, beam design. So now the software is calculating in function of the parameters you inputted, and it will give you the calculation and your new reinforcement and rebars for the beams. Okay, now in this window that appear, you can sort by member. So if you click here, you will view all the members in your model. So you see that in my model here, everything seems to be okay. So that's great. And if you check by property, the software will only display the property of the beam, of one beam. So now you can do also the column design. So let's check the column. Okay, now I got all my column which has been designed, so let's check everything. So everything seems to be okay. So in case it's not okay, it will display in red and you will have to redesign this. So you have recalculation, and if you want to design for one specific member, you can do design criteria for rebar by member. So using this option you can design for only one member, so it's very useful. Now let's do the wall design, and same, we get all the different shear walls. And what is also very interesting is the graphic. Oh, I have to select, okay, so I have to select the wall and display the graphic, and now you have a view of the different parameter which has the most important here. So they are all okay for this wall. You have the PM interaction diagram and the shear force capacity check as well. And that's all for this tutorial today. So I hope you enjoyed it, and see you next time for the next tutorial on Midas Gen.